Hello everybody. Today we are going to be solving this rotational motion question, and this is from the book Pathfinder. And this was in one of the easiest sections of Pathfinder, but I found that this question is also very challenging, and I can say like 99% of people won't be able to solve this question. So Pathfinder is not a like joke book. It has pretty difficult questions, and this one is also pretty difficult, I'll say. Not very difficult, but pretty difficult. Okay, so let's read the question. A disk is placed on a frictionless horizontal plank and is rotating with a constant angular velocity omega about its central vertical axis. Now the plank is made to move with a constant acceleration a on a straight path. Okay, so if you assume and there is no friction, so the disk won't move with the plank. Okay, it will just fall off the plank, or you'll say it won't move with the plank, it will stay where it is. Okay, so if you assume initial location of the center of the disk as origin, direction of motion of the plank in negative y-axis. So if you assume initial location of the center of disk as origin, so let's just draw a little bit of the diagram. So we have this disk, and there's this plank underneath it, and the plank, what it is doing is um, it is going in the negative y-axis direction. So let's say the plank is going here, so the disk, it will go here. Okay, or you can say relative to the plank, the disk will go upwards, so like in the positive y-axis direction. So if the plank is going in the negative y-axis direction with an acceleration a, then a person sitting on the plank would see the disk going with the acceleration a in the positive y direction, right? So that is the concept of pseudo force. So if the plank is moving with acceleration a in the negative direction, negative y-axis direction, then the person sitting on it will see, or relative to the plank, the disk will be going in the positive y-axis direction with acceleration a, right? Okay, so we can get the and in the question they are saying that the coordinate system is attached with the plank. So which of the following equations represent trajectory of instantaneous center of rotation of the disks? Oh, so they are asking which of the following equations represents trajectory of instantaneous center of rotation of the disk. So we need to find basically the like instantaneous center of rotation of the disk. So now this is a new concept. There are two things, ICR and IAR. This is instantaneous center of rotation, and this is instantaneous axis of rotation. So basically, in short, ICR is basically a point, it's a point which has zero velocity. So this point has no velocity, and relative to disk, relative to this point, the CRTM, or the CRTM that an object is performing, that is just a plane rotational motion. So for understanding, if you have this inclined plane and like a disk rolling down, okay, so then this point is your ICR, which is the instantaneous center of rotation. How is it the ICR? Relative to this point, like this disk as a whole is doing rotational motion as well as translatory motion, but relative to this point over here, this instantaneous center of rotation, what this point can see is the disk just rotating. And as you know, its velocity is zero if the disk is rolling down. How? Like it has over here r omega, and in this direction it has velocity v, right? So if the disk is going with v, so it has v over here, r omega over here, and also acceleration, it has r alpha, that is equals to a, and a down, like this. Okay, this is our plane CRTM, or rolling on an inclined plane. Okay, so as so now let's move back to the question. So we need to find the equation which represents the trajectory of instantaneous center of rotation of the disk. Okay, so now this instantaneous center, as you can see, is not on the disk itself. It can be these ICRs and IAR can be on the disk or can be outside of the disk also. Okay, so let's move back to the question. Let's try to understand what is happening. Okay, because the language is a bit confusing, so let's try to understand what is exactly happening. Okay, okay, I'll just rub all of it and then like start over. Okay, so we have this disk. Now on the plank on which it was, the coordinate axis is on that plank. So if that plank goes in the negative y direction with a, the disk is going in the positive y direction with acceleration a. So this is the positive y, and let's say this is the x, right? Even though we don't need the x direction, so let's just keep this part. Okay, and it's also rotating with omega. So in the options, this is a multi-correct option. So omega k means like this. So this is the positive y, we can say. So omega, this is the k direction, right? This is the k direction, and this is basically where the disk is rotating with omega. Now anti-clockwise is positive conventionally, and like clockwise is negative, right? So if we are saying omega equals to omega k, and where omega is positive, then we are going to take it as the disk rotating in the anti-clockwise direction, and if we take negative, then that is in the clockwise direction. Okay, so we have to do this once for positive, once for negative. Okay, so this disk from top view, let's say it's going in the anti-clockwise direction with omega angular velocity, right? So with omega angular velocity, it is going in the anti-clockwise direction. Now what is happening? Let's look at this point. This point has a velocity of r omega over here, and then this point is accelerated also. This point on the other hand has r omega like this, and it has acceleration in the opposite direction, right? So this point has its velocity increasing, and this point has its velocity decreasing. Why? Because for this point over here, acceleration is in the opposite direction, whereas for this point over here, acceleration is in the direction of its velocity, right? So this is a complex CRTM. Just try to imagine like one part of the disk is speeding up, the other part is slowing down. So from the center, now obviously the center does not have zero velocity. We need to find a point where there is zero velocity, and relative to which the disk is performing pure rotation motion. So if you just try to imagine this thing, this whole what you say, uh, this whole thing will like somewhat go like this. If you try to imagine, it will go somewhat like this. Why? Because this is increasing, this is decreasing, so it is somewhat inclined to go over here, right? Because this is rotating like this, and it is somewhat inclined to go like this. Just try to imagine, visualize that in your head. What basically the basic principle says, like ice of ICR, instantaneous center of rotation, that it will always be close to the point where the velocity is less or very less or decreasing, right? So over here, as you can see here on this point, velocity is decreasing, so you can say that instantaneous center of rotation is somewhere over here. Okay, and if you try to imagine, the disk will go something like this. Just try to imagine. uh okay, so let's see. Now let's make this again. Okay, okay, So over here, let's say, so we know that the distance cover will be ut, initial velocity is 0 plus half at square. So this is the distance that the disk will cover in t time, and its velocity in t time will be at, right? Right. And now let's say ICR is over here, instantaneous center of rotation. Let's say this distance is let's say x1 or x naught. Okay, so this is the distance x naught. So as this is the instantaneous center of rotation, x naught into omega equals to velocity. How? Because this the pure rotation motion is happening, and when pure rotation happens, we know that radius into omega equals to velocity. So similarly, x naught into omega equals to the velocity of the disk. All right, now we get that x naught equals to v by omega. So x naught equals to at by omega, right? X naught equals to at by omega. Or let's say we need to get rid of t, right? Because in the equation of trajectory we do not have any t term. So t equals to omega x naught by a, right? And then we are just going to put it over here in s. So we had s equals to half at square a, and then omega square x naught square by a square, right? A cut. So we get s equals to omega square x naught square by 2a. This is what we are getting, right? So this is what we are getting when we took the omega velocity in the anti-clockwise direction. So like for positive omega, so we were checking for option A and C. Oh, sorry about that. We were checking for options A and C, and we get y equals to omega square x square by 2a. So it's the option A is correct. And it is also saying that x is less than 0, less than or equals to 0. So basically it's asking that where is the instantaneous center of rotation. Obviously, if this is the y direction, sorry about that, if this is the y direction, positive y direction, so this is the positive x, this is the negative x. So this negative x over here, the instantaneous center of rotation is located, right? So that's why a option is correct, where x is less than 0, less than or equals to 0. Now if omega equals to minus omega k, so if the rotation was happening in the clockwise direction, then what would have happened? If this rotation was happening right in the clockwise direction, so let me just show you. So rotation is happening in the clockwise direction. This would be r omega over here, a over here. This velocity is decreasing, so instantaneous center of rotation is in the positive x-axis, right? It is in the positive x-axis. And even though we have negative omega, in s we have omega square, so negative omega square is basically omega square, right? So the equation of trajectory won't change, but x is on the positive x-axis, right? So the equation of trajectory remains same and x is on the positive x-axis. So the correct option is A and B. These are the correct answers. So A and B are the correct answers of this question, and I hope my explanation was apt. I think I explained it pretty well. I hope you understood the question. They were asking equation of like trajectory of instantaneous center of rotation. Now, first of all, you need to know what that is. Before this question, let me be honest, I also didn't know what ICR and IAR is. So ICR is basically the point relative to which, if a body is performing CRTM, relative to that ICR, it is like just doing rotational motion, right? if you sit on that ICR point, or like center of rotation, instantaneous center of rotation, then you will see the body just doing rotational motion and no translation motion, right? That's ICR, and the axis passing through it is called IAR, which is the instantaneous axis of rotation, right? So now after that we solved the question pretty well. We also saw that ICR is close to the point where velocity is decreasing, obviously, and that's a bit obvious also if you try to picture it. And then we just use normal equations of motion, as we found the distance. We know v equals to u plus at, and then we know that we know this, that x naught into omega equals to v. Now x naught was the distance of the ICR with the center of the disk, or with the axis on which the disk was rotating. So we got the value of x naught, and we already had the value of v equals to 80. So we substituted t in this equation. We substituted t, and then finally we got the equation of trajectory. One thing to remember is that in the equation of trajectory, there is no term of t. So that's the speciality, that it has no time term. Okay, like in kinematics also we have the equation of trajectory, it also does not have the term of time, right? So I hope you like this video, guys. The answer is A and B, and this was in the MCQ part of Pathfinder, and I think that that's the simplest section of that book, and the question wasn't that simple. So Pathfinder is no joke, and I'll see you in the next video, guys. Thank you.